but if not, I would like to share with you that our Neurotraining Academy has a new look and feel to it. Our NTA platform has become more engaging as we continue to provide you, our members, with direct access to the latest educational content in neurodiagnostic, neurocritical care, and neurosurgery, all in one comprehensive location. So check us out at neuro-training.academy. Today's webinar is entitled EEG Basics Instrumentation and is part one of a two-part series. Part two on electrocerebral silence studies will be presented on June 30th, 11 a.m. New York time. So please register for this webinar as well. Both of these webinars have been approved for continuing educational credits by the ASAT Neurodiagnostic Society. I'm Dr. George Grazia, Global Medical Education Manager, Neuropathways, and I'll be your host for today. Before we begin, I would like to share some meeting details in which all of your lines are muted to manage background noise during the presentation. We will allow time for questions at the end of the presentation, so please type your questions into the box on your screen. This meeting is also being recorded and will be available for viewing at a later date on our Neurotraining Academy website. Our speaker today is Melissa Struing. Melissa is a professional educator and trainer, board certified in EEG, evoked potentials, intraoperative monitoring, and continuous long-term monitoring, and offers 14 years of clinical experience in the area of electroneurodiagnostic technology. She is currently the END program director at Sinclair Community College in Dayton, Ohio, focusing on END courses while also chairing the advisory committee. She has trained numerous professionals, including technologists, nursing staff, and various students. In this webinar, Melissa will present a detailed discussion of EEG instrumentation, including sensitivity filters and time base, along with the rationale for changing the settings for optimal recordings in various clinical settings. So without further delay, it is my pleasure to introduce Melissa Struing. Melissa, please.
Hello, and thank you all for being here today. I'm going to turn off my webcam so you can see the screen a little bit better. And as George has said, today we are going to be talking about just some basic instrumentation for the next hour, reviewing sensitivity, filters, and time base. So let's get started. So the big idea, the whole purpose of today's webinar is to help you understand how to change your settings to be able to better view the EEG. And we're going to do that by changing these basic settings: our low frequency filter, our high frequency filter, the notch, the sensitivity, and the time base. So for our learning objectives for today is that after this presentation, that you will be able to define sensitivity, filters, and time base, be able to describe the effects of low, high, and the notch filter, be able to explain why we change sensitivity and to discuss reasons for changing the time base. And then one thing I do want you to remember as we're going through everything, when we are changing these settings, we're only changing the appearance of the waveforms. We're not actually changing the waveforms themselves. Okay. So here, before we get started, I just kind of want to take a quick poll to see how many of you guys are actually comfortable changing your settings.
Okay, so we're going to launch the poll. Here are the questions. And here's the question with the choices. So we'll launch this poll. And you can pick your answer, and we'll see what our audience thinks so far in the beginning of this presentation. Please choose your answers. Okay, we're doing very well. We're about 30% have responded. Okay, about, oh, wow. Okay, so right now I'm going to close the poll. And I'm going to share the results with Melissa and the audience so we can see what the results show. So here are the results, Melissa, for you to review.
Okay, I do not see the results.
You don't see the results?
Mm-mm.
Oh, okay. They have 60% I changed sensitivity in some filters. And 18% I changed sensitivity. 12, I never changed my sensitivity. And 14, very comfortable, uncomfortable. I always change my sensitivity. So it looks like 60%. I change sensitivity and some filters.
Okay, well, that's really good. It's always good to change those. And if you don't change them, hopefully by at the end of this presentation, you will want to change them. So,
Okay. So here we go back to your slide. Continue, please.
Okay. Thanks everyone for participating. We will have about 5 more polling questions throughout this presentation as well. So if you are not already familiar with the American Clinical Neurophysiology, Society or the ACNS guidelines, I really highly recommend that you review them. A lot of the definitions and settings discussed during this presentation come directly from those guidelines, specifically Guideline 1 for today's. And if you are sitting for your ABRET EEG board exams, these guidelines will be on your board exam. So even though your facility may do something else, the most correct answer are going to be directly from these guidelines. Okay. So what we're going to do is we are going to start talking about sensitivity first. So according to the ACNS guidelines that I just talked about, sensitivity is defined as the ratio of input voltage to trace deflection. So what that means is that the sensitivity is equal to the input in microvolts that is received from the brain. The input coming from the brain over the output of the deflection that you actually see on the EEG itself. So again, that's just input from the brain over the output that you will see on the EEG, and that equals sensitivity. Sensitivity is measured in microvolts per millimeter, and it's usually set between 5 to 10 microvolts per millimeter, and most machines are defaulted to 7 microvolts per millimeter. Here at the bottom of your screen, the bottom left-hand corner, you're going to see this chart, and it shows you the relationship between sensitivity, voltage, and deflection. So this top line here where it says voltage of this line, that means divisions, and I guess I should have put a division sign there. So sensitivity equals voltage divided by deflection. And exchange, deflection equals voltage divided by sensitivity, and voltage equals sensitivity divided by deflection. And we are going to talk a little bit more about that here in just a moment. So sensitivity just really changes the appearance of the amplitude of all the waveforms. It doesn't change the voltage or the frequency. It only changes the way we see these waveforms. So when you think of sensitivity, which I see that most of you were very comfortable already changing it, you can, again, think of it as a zoom function on your camera. You can zoom in into a picture to see things closer up, or you can zoom out to see things a little farther away. So in this picture, it's a picture of my daughter, and you can see right here at the bottom, it's just a picture of her head, right? So that would be with our standard sensitivity, 7 microvolts per millimeter. We can zoom out to make it appear farther away, and now we can see her legs, her body, or we can zoom in and just see her eye. And notice my daughter didn't actually change, just the way we changed the viewing of her changed. So we zoomed in or zoomed out. And the same is true with the sensitivity. Again, it doesn't change the voltage of the waveform. It really just changes how we view it and what we see. Okay, so here's an example of some EEG. So you can see in the first picture that sensitivity is at 2 microvolts per millimeter. The middle picture right here is at 7 microvolts per millimeter, which is our normal setting. And again, between 5 and 10, normally at 7 microvolts per millimeter. And this last picture is at 20 microvolts per millimeter. The lower the number here at 2 microvolts per millimeter, all the way on the far left of your screen, the taller or larger the waveform appears. So this is just with our zoom in from our camera analogy, they appear larger. The higher number of the sensitivity over here on the right side of our screen at 20 microvolts per millimeter is the shorter or the smaller the waveform appears. So this would be the zoom out feature for our sensitivity. But what I do want to note that it's very important when we're talking about sensitivity, because there's a lot of confusion when we talk about some of the terminologies for sensitivity. So when we talk about decreasing the sensitivity, we are actually talking about decreasing the visualization of the waveforms. So what I mean by that is if someone says, can you decrease the sensitivity on this EEG? Here, in this example that I showed you, you would change it from 7 microvolts per millimeter to 20 microvolts per millimeter, actually increasing the number, but decreasing the sensitivity. In contrast to that, if you were asked, if someone says, hey, can you increase the sensitivity on this EEG? They're just referring to increasing the appearance of the amplitude of the EEG. So here, we would change the sensitivity from 7 microvolts to 2 microvolts per millimeter, lowering the actual number of the sensitivity. So again, if we want to increase our sensitivity, we want to use a lower number, making the waveforms appear larger, more sensitive. If we want to decrease the sensitivity, we want to use a larger number.
Ué, meu som não tá aparecendo? O que aconteceu? Espera só um pouquinho.
Ano ఒకసారి ఆపుదాన్ని ఆపుదాన్ని దాన్ని
Okay, I'm unmuted. Okay, can you guys hear me? Okay, I apologize for that. I'm not sure what happened. So I'm going to restart over with this slide. So I'm not sure where you guys...
Yeah, a little technical difficulty there. Apologies.
So again, sensitivity. So again, here is an example of the sensitivity of an EEG. You can see here in the first picture, all the way on the left-hand side, the sensitivity is at 2 microvolts per millimeter. The middle picture is at 7 microvolts per millimeter, which is what we normally see our sensitivity set at, usually between 5 and 10. And then here, all the way on the right side, is the sensitivity of 20 microvolts per millimeter. As you can see, the lower the number, all the way on the left at 2 microvolts per millimeter, the taller or larger the waveforms appear. This is our zoom in feature from our camera analogy. On the right-hand side, at 20 microvolts per millimeter, the waveforms appear shorter and smaller. This is our zoom out feature for our sensitivity. And again, I know I'm not sure if you guys heard me or not, but when we talk about sensitivity, a lot of my students, when they're first learning, get very confused about some of the terminology because it's a little bit confusing. So when I talk, or if somebody says, hey, can you decrease the sensitivity? We are actually talking about decreasing the visualization of the waveforms. So if someone said decrease the sensitivity, in this example, you would change it from 7 microvolts per millimeter to 20 microvolts per millimeter, actually increasing the number for the sensitivity, but decreasing the amplitude of the appearance of the waveforms. Contrarily, if you're asked to increase the sensitivity, again, this is just referring to increasing the amplitude of the EEG. And here it would be changing the sensitivity from 7 microvolts per millimeter to 2 microvolts per millimeter, actually lowering the number of the sensitivity. So again, if we want to increase the sensitivity, we want to use a lower number, making the waveforms appear larger, making it more sensitive. And if we want to decrease the sensitivity, we want to use a larger number for our sensitivity, making the waveforms appear smaller and less sensitive. I know that this can be kind of confusing at first. So if you kind of review it and figure out what they're actually asking you, it starts to make a little bit more sense. Okay. So I told you that a few slides ago that sensitivity is defined as a ratio of input voltage to trace deflection. And this equation, again, on the bottom left-hand side is just how they're related. So sensitivity equals voltage in microvolts divided by deflection in millimeters. So even though we do change the sensitivity and the height of the waveform changes, the actual voltage of the waveform coming from your brain remains the same. So if you're studying for your AREP board exams, you'll need to know this equation and how to solve it. Usually sensitivity is something that's known, so usually you're solving for voltage, but today we're going to just be discussing sensitivity and using it, but you can kind of see how it works backwards too for deflection. So in this example, so here's the same picture of the EEG, and I just blew up one of the channels here. So the voltage from your brain, the brain activity is at 30 microvolts per millimeter. We see the sensitivity is set to 7 microvolts per millimeter. So in order to represent that voltage on the screen at that sensitivity setting, you would need a 4.28 millimeter waveform. So if you took your millimeter ruler out, you could just measure that waveform and it would be 4.28 millimeters. So all the people who were on used paper EEG or had old oral exams, they would give us a sensitivity. We would measure the waveform and we would have to figure out the voltage, which voltage would be sensitivity divided by the deflection. So we could try to figure out the voltage. But you can see the relationship with the amplitude of the waveform with the voltage from the brain activity and how the sensitivity makes it appear larger or smaller here. Okay, so now we still have that 30 microvolt voltage from brain activity, but we change our sensitivity to 2 microvolts per millimeter. So here it will take 15 millimeters to represent the true amplitude of that waveform coming from the brain activity. So it makes it appear larger on our screen. So here, as you can see, we get the number of the deflection by using that same equation. So we take 30 microvolts, which is the voltage, and we divide it by 2 microvolts per millimeter, which is our sensitivity setting, and we get 15 millimeters. So that's why the waveform appears larger. So the voltage is actually the same, it just appears larger because our sensitivity setting is different. You can tell from that, from our equation. Okay. So, and again, in this example, we're just changing the sensitivity to 20 microvolts per millimeter, and we still, again, have that 30 microvolt voltage the activity coming from the brain. And we know that waveforms look smaller the higher the number. We're zooming out. So when we decrease our sensitivity to a higher number, we can also expect that we're going to decrease the millimeters necessary to represent that waveform on the screen. And we know that because we can plug it right into our equation. So here we take our 30 microvolts and we would divide that by 20 microvolts per millimeter, which is our sensitivity setting, and we would get 1.5 millimeters. In turn, if we were trying to figure out what the voltage of these waveforms are, we know the sensitivity, we would multiply that by the height of the waveform. So you could just take your millimeter ruler out, and really now in digital, you could just click on the top of the wave and the bottom of the wave, and the computer actually will tell you what it is, and you can figure out that equation. But it is important to know this equation if you are sitting for your board exams. Okay. So again, the sensitivity is set by default to 7 microvolts per millimeter, and it's really important that when we all are comfortable. They're hotkeys for sensitivity for the up and down arrow if you're using Natus. That you just kind of make sure that you glance and look at those sensitivity settings because it can easily be changed. I've had it happen before, and we can think that the recording is actually a higher amplitude or a lower amplitude. I've definitely accidentally hit those hotkey buttons and looked like, wow, this is a really low voltage waveform. But in reality, the sensitivity had changed. And it wasn't actually the patient, it was the setting. So it is really important to make sure that you look at your settings accordingly. Okay, so here's another example of why we like to use sensitivity. It can help us define these waveforms. So here's an example. You see something's happening. What is it? You don't know. Our sensitivity setting is at 7 microvolts per millimeter. We increase our sensitivity to make it more sensitive. Oh, that just makes the waveforms appear larger. That's not really going to help us. Now we change our sensitivity to 20 microvolts. So we decrease our sensitivity. Now we're able to count how many of these spike and wave complexes are there. And then it will also help us to determine if this is a generalized epilepsy, if it's 3 hertz spike and wave, is it absence, is it something else, is it a slower? So our sensitivity, changing it will help us to be able to visualize those waveforms and help make a better decision when we're looking at the EEG. Okay, so again, another way to look at this, the lower the number of the sensitivity, the more sensitive it is, the higher the amplitude of the waves appear. The higher the number for your sensitivity, the less sensitive it is, the lower the amplitude of those waveforms appear. Okay. So what I want you to know about changing the sensitivity is that changing the sensitivity only changes the appearance of the waveforms. The actual brain waves are still exactly the same. And I do want you just to make sure that when you're reading an EEG, when you're sitting down to look at it, just glance up, look at those sensitivity settings to make sure that you're reading it appropriately. Because again, if it's set at 2 microvolts per millimeter, you conclude that they have a really high voltage EEG, high amplitude. And if it's at 20 microvolts per millimeter, you could conclude that it's a very low amplitude EEG. Okay. So now we are going to do a another polling question for you guys to see
Okay,
if everybody's getting this. Yep.
so we're going to do a poll question. I think if you can see, if you open your audience view pane, Melissa, I don't know if it's open or not, you will probably be able to see the questions.
Okay. Yep.
Okay, and there was some background noise typing. I don't know if it's where it's coming from, but it's certainly not coming from my end here. So I don't know where so we'll hopefully we can eliminate that. But here is the question, and let's launch this poll and see what our audience thinks. Which is the most sensitive setting? So we have a tremendous number of people in the audience. So let's see what they say. It's going very well. We're about 65%. Okay, so we're going to close the poll, and here I'll share the results. So here are the results. Interesting. 75%, 2 microvolts per millimeter.
Okay.
Very good.
Yep. So you guys are right. So this is a common board question that you will see is what is the most sensitive setting? And you are absolutely right. 2 microvolts per millimeter is the most sensitive setting because it makes those waveforms appear the largest. 3 microvolts is just our voltage. So that has nothing to do with sensitivity. We can eliminate that one immediately. 7 microvolts per millimeter is our normal standard, and 20 microvolts per millimeter will zoom out. It will be the least sensitive in this example because those waveforms will appear the smallest. Okay, so here is polling question number 3. And this is, what can you change to view the following EEG better? So kind of look at this.
Okay, give you a few minutes. So I will launch it with the same choices. Here are the same choices for that EEG. And let's see what our great audience thinks now. Okay. Taking a little longer on this one. Okay.
I know sometimes it's hard to see those settings at the top of the screen.
Okay. Okay, we have about 60%. Okay, I will close it and see what are the results show here. Okay. Oh, wow. Here are the results.
So let's see. So we have a little bit of everything, right? So we have some in every single category. Okay, so let's put it back to presentation and I will explain that. So when we talk about better viewing this EEG, if you notice up at the top, and it may be a little bit hard for you guys to see right here, the sensitivity is actually 30 microvolts per millimeter. So the best answer would be changing the time base. We haven't talked about time base yet, so changing the time base, it could affect it, but since we haven't talked about it, that's probably not the answer for this case. But if we change our sensitivity to 7 microvolts per millimeter, as you can see here what I did, you're able to see that. You're able to count that posterior dominant rhythm to see what is happening. If you change sensitivity to 2 microvolts per millimeter, it's going to make it even, I should have made an example and I didn't, and I apologize. It's going to make those waveforms appear larger, and you might not be able to read that EEG because those waveforms are going to be running into each other. Changing the sensitivity to 20 microvolts per millimeter, yes, that would improve it. It would make it more sensitive. However, there is a better answer for that, and that's why 7 microvolts per millimeter is the better answer. And does it look good? Yes, you can see it, but this, you can see it a little bit better. You can see more of those details. So good job, everybody. Okay. So now we're going to move on and we're going to talk about time base. So the time base or display screen refers to how much of the EEG you are actually seeing on the screen at the time. It's normally set to about 10 to 20 seconds per page, but nowadays it really just depends on the size of the monitor you are using. I've seen people use big screen monitors to review EEGs, and you can get a lot more data on those types of monitors. And also, depending on the manufacturer, some people will just do it by seconds. So they'll say just 10 seconds per page or 20 seconds per page. But the 10 seconds usually is roughly corresponds to a paper speed of 30 millimeters per second on like the old paper system. And that's usually what we are using today. So even in the ACNS guidelines, you'll see that it will say about 10 to 20 seconds per page or 30 millimeters per second. So the analogy that I like to use for the time blaze or the display is an accordion or a slinky. If you're younger and maybe not know what an accordion is. So what you do with that, you stretch it out or you bring it really close together, but everything stays the same. You don't add any pieces to those. You don't take anything in the way. You just change again how you view it. The same is true with the time base. When we change our time base, we don't change the frequency. We only change how condensed or spread out it looks, or how congested, how close together it looks. So here on this graph, you can see two dark vertical lines right here where these arrows are pointing to at the very top of those, and they represent 1 second. So when I talk about 30 millimeters per second, what I mean is if you held up your ruler at that second, at that distance, you would have 30 millimeters in 1 second. So here on this ruler, you can see here with the red line, 10 millimeters per second. That would mean that this would be nice and condensed, like I said, for 1 second. This at the 1 would be your mark per second. At 20 millimeters per second, we would be at the 2, and again, a little bit farther away, not as condensed, but still condensed. 30 millimeters per second. Again, take out your ruler, it's just, that's how much is in a second. And then, which is our normal, and then we would have 60 millimeters per second, and that would be much more condensed, much more spread out. You would expand it a little bit more to get all those in. And we'll talk about why we would want to do that. So, like I said, our normal time base, and with Natus equipment, Excel Tech, they use time base, they use millimeters per second. And here we have our normal time base for 30 millimeters per second. You can see the legend. So we know that this is important, and we use our time base a lot, our horizontal axis, just to count our frequency to visualize those waves. So this is normally what we're looking at, and it's about 10 seconds per page on the monitor. Now here I changed the time base, same page, to 10 millimeters per second. So here you can see that there's much more data on the screen. It's much more condensed. It looks much different than this page right here. And the reason that we would want to change this, why we would want to make it more condensed or more scrunched up, is because one, we can better see slow waves. You can see more of the slow waves on the screen. You can also change this for somebody's in burst suppression, so you can count the bursts easier because you have more of that data. This is also the way that they look at it in sleep for other examples. But that is just some of the reasons that you would want to change your time base. But again, if you work in pediatrics with neonates, a lot of times they will have a 10 millimeter per second or a 15 millimeter per second time base so that you can see those slow waves a little bit more scrunched up on that screen. Contrarily, we could increase our time base and make it more spread out to 60 millimeters per second. So this would look a lot further apart. And really why we would do this, spreading it out, helps us to see faster waveforms. It helps us to calculate the duration of the waveforms sometimes. If we want to get theoretical, say if you had a 60 hertz, and we'll talk about 60 hertz here, you could change your time base so that you can actually count out those 60 hertz, those faster frequencies, to prove that it's 60 hertz without actually turning on your notch filter. I don't know why you would do that, but you could do that. So that's what it helps. It helps us to count the frequency, especially of those faster frequencies, because it spreads it out. It helps us to determine the duration of the waveforms as well when you change your time base to 60 millimeters per second. Okay, so here is another just a screenshot. You can see an example of each of those ones. Here is a time base at the top, 15 millimeters per second, so it's much more condensed. Here in the middle is what we're normally used to looking at, 30 millimeters per second. And then here at the bottom is expanded a little bit more at 60 millimeters per second. So when we change our time base, it just changes how many seconds are on the screen, and in turn just changes how much EEG data is on the screen at a normal time. So again, just to recap what I just said. So normally when we change, our time base is set to 30 millimeters per second, or about 10 seconds per page. And when we change our time base from 30 millimeters to 60 millimeters per second, we see less data on the screen. It stretches those waveforms out on the screen. And again, this is best used to visualize faster waveforms, those faster frequencies, to be able to count those. And then we can see where the faster components begin or end a little bit easier at what time. And we can also count those faster frequencies. And it also allows for better calculation of the duration of the waveforms. So when we change our time base from 30 millimeters per second to 10 to 15 millimeters per second, we see much more data on the screen, and it appears much more scrunched up, right? Much more closer together, which we're not allowed with this coronavirus, right? We have to keep a little bit farther apart. So the reason why we would change it from 30 millimeters per second to 10 or 15 millimeters per second is because it allows us to better visualize those slower waveforms, and you'll be able to see them on the screen more. So that is why you'll see a time base of 10, again, like I said, 15 milliseconds on newborns who have slower waveforms. You'll also be able to see it if somebody has a slow focus somewhere. If you change your time base a little bit, you'll be able to see that slow focus a little bit more. It will pop out a little bit. So if you don't change your time base when you have some like just lateralized slowing or focal slowing, go ahead and experiment and change that and see how it looks different on the EEG. You might find that you enjoy, again, not permanently to run the whole EEG like that, but just for a little bit to experiment and see how that looks. Okay, so let's see our polling question number 4 about time base. So what setting would you change to get more burst on one screen in the EEG?
Okay, so let's see what the results are here. Okay, I'm going to close. Interesting again.
Okay, good. So we have a little bit of everybody. The majority of you guys said to change the time base to 10 millimeters per second, and you are absolutely right. So we would want to, if we want to see more burst on one screen, that means we need to see more data on the screen. That means we need to shorten our seconds so we get more seconds. So if we change our time base to 10 millimeters per second, we are going to see more of those on the screen. So here is what the sample looks like. And now you can see more of those bursts when we change it to 10 millimeters per second. Changing the time base to 60 millimeters per second spreads it out. So you're going to see less data on the screen. Changing the sensitivity doesn't change the amount of data on the screen. It just changes the amplitude. And keeping the time base at 30 millimeters per second does not get us more burst on the screen because that's the setting that it was already at. So really good job, everybody. Okay. So now we're going to discuss filters. Now this is everyone's favorite subject. And we're back on time, so I can slow it down, I think, a little bit. So when we talk about filters, we all use filters in our everyday lives. We use coffee filters, air filters, water filters, and the list can really go on and on and on. And all these filters help to eliminate unwanted things. For example, coffee filters help you to eliminate coffee grinds. You don't want those in your cup of coffee, right? The same with the other filters. They get rid of something to make something else better. Our filters are the same way in EEG. They can eliminate something we don't want to see to make our EEG look better, or they can enhance it to bring it out a little bit more. So there are 3 types of filters that we are going to talk about: the low frequency filter, the high frequency filter, and the notch filter, or the 60 hertz filter here in the US, 50 hertz filter in other parts of the world. And it's really important that you know how to use your filters. You want to know it because you want to be able to change them to enhance the viewing of your EEG, and also because improper use of filters can prevent you from recognizing EEG abnormalities, artifacts, or other changes that occur during the EEG. So if you use them improperly and you're not using them right, you can miss some things. Okay, so here is just kind of a rough graph of low and high frequency filters. So here on this vertical line, or the you will see the amount of amplitude of the wave you will see, and here on the bottom you will see the frequency. So this is actually what's our bandwidth. Are we an alpha? Is it alpha wave, a delta wave, theta wave, whatever it is. So what I want you to take away from this picture is that each filter will generate a certain amount of amplification of the waveform. We'll see a certain amount of a waveform with each filter. It can do one of three things. It can be seen at 100% of the waveform, therefore it passes through, so none of the waveform, all the waveform is seen. Or it could stop the waveform. The filter could stop the waveform so that none of the waveform is seen. Or there's that middle yellow area where a percentage of that waveform can be seen. And I'll talk about this a little bit more as we go on. But I do want to say, so the filters, when we change the filters, depending on, the filters only affect certain frequencies. So the low frequency filters only affect low frequency filters. High frequency filters only affect those. Depending on which filter we're going to use, it's going to change those waves. So it's either going to stop the wave, so you're not going to be able to see it. You're going to be able to see a percentage of it, or it's going to pass through. You're going to see 100%. It's not going to affect those waveforms. I do want to note that there's a major difference between sensitivity effect and the filter controls, are that the filters only affect specific frequency, whereas if you change your sensitivity, it affects the amplitude of all frequencies, whereas filters only affect certain ones. Okay, so let's dive in and have some fun with these filters. Okay. So low frequency filters, they have very many names. You'll hear them called high pass filters, low cut, time constant. It really just depends on the manufacturers. No matter what the name, they all only affect those low, slow frequencies. They're called high pass filter as well, because those higher frequencies can pass right through unaffected. You're going to see them at 100%. It's not even going to touch them. Those low frequency filters are also called, in some machines, low cut, and some literature low cut, because essentially it will filter out low frequencies below that set value. That's not 100% true, but kind of the gist of it, like, oh, anything below whatever that frequency filter is going to be affected. You're not going to see it off. You're going to cut off those frequencies. The default setting for most machines for the low frequency filter is 1 hertz. The ACNS guidelines that I talked about at the beginning recommend that a low frequency filter setting higher than 1 hertz should not be used routinely, as vital information could be lost when pathological activity in the delta range is present. So if you keep your high frequency filter on the whole time, you can really miss some important waveforms. And I know with digital, you can go back and you can change it after the fact, but when you're seeing it live with that EEG, you don't want to miss some of those important things. Your neurologist will not be happy with you if you don't call him if you see something. Okay. So here is an example of a frequency response curve. Note that this is just really a rough representation. So what is a frequency response curve? Well, it's just really a graphic representation of the effects of a filter on the amplitude of that frequency. So this curve, so right here you see this black curve. So when we talk about the curve, and I didn't make as many curves, I just did one, you can see that this is a 1 hertz filter. And it's a frequency response curve because this filter curves and affects different things. And these curves are specific to each manufacturer and whichever specific equipment you're going to be using. So it's going to change depending on what type of equipment you have. So in this chart, again, this y-axis right here, you'll see 0% at the bottom, 100% at the top. This is a vertical line. It represents the amplitude, how much of the waveform you're going to see. here at this horizontal line, this x-axis, it's going to represent the frequency, those actual waveforms you're going to see. And again, this curve, this black line is representing your filters. So to use this chart, to use a frequency response curve, you simply take the frequency in question. So let's say I'm going to use 1 hertz. So that's the hertz. So I have a 1 hertz delta wave form, right? And then you're just going to run your finger up to where it meets the curve, right here where the screen line is. And then you're going to go over and go to the percentage of that waveform where it touches. And then that's going to determine the output of the amplitude that you will see on the EEG. So in this example that I just told you, you'll have a 1 hertz. The 1 hertz filter is on because I told you, and that's what's represented by this line. And I will find the 1 hertz waveform on the x-axis. I will go up to where it meets. Then I will go over to the y-axis and I will see 70%. And this is going to tell me that a 1 hertz wave will be seen 70% of the time with a 1 hertz filter on. Again, this will vary by manufacturer, okay? So again, with a 1 hertz filter on, I will see a 1 hertz wave at 70% and it will be attenuated or not seen at 30%. Also, what you'll notice with this curve here, it goes down to say maybe 0.2, right? This is a 2 scale of a chart. But down here at the bottom, the numbers to the left of this, where it goes, will be attenuated or seen less. So this 1 hertz waveform will filter out all these really teeny tiny low waves, anything less than that. Now, you'll also see frequencies to the right of this low frequency filter at 1 hertz. So say, I don't know, 5 hertz. None of it is going to be affected. You're going to see that at 100%. Okay? So again, if I have a 0.0 hertz wave, I'm going to see very little or none of that wave is going to completely stop it. But if I have a 10 hertz waveform with the 1 hertz filter on, I'm going to see 100% of it. It's not going to be affected at all. So anytime that you have a specific frequency that matches the filter, it will be seen at 70% and attenuated or not seen at 30%. So it equals at 100%. So if I have a 3 hertz delta wave and I have a 3 hertz low frequency filter on, I will see that waveform at 70%. All the waveforms below 3 hertz, so the smaller the number, will be attenuated more, right? I will see less of them. They will be stopped. The ones to the right, I will be seeing more. So if I have a 5 hertz theta wave and the 5 hertz filter is on, I will see that waveform at 70%. So when the filter matches the frequency, you're going to see it at a roughly 70%. Okay? Now, I know when you're sitting for your board, they don't show you frequency response curves anymore, but it is kind of important to understand them. And we don't have time to go through there. I can spend a whole hour just on frequency response curves. So if you have questions about it, you can feel free to email me as well. So here is just another way to look at it, because I know a lot of people are like, oh, that graph you just showed makes me so anxious. If they're not going to show it on the boards, why do I have to know it? Well, here's another way to look at it. So here's your low frequency filters. And here you can see at the top of the screen, you have your 5 hertz filter. And then here at the bottom is a 0.1 hertz filter. And again, normally we're at 1 hertz. So the higher the number of the low frequency filter, the more frequencies below it are going to be attenuated or seen less. So if I have this 5 hertz filter on and I say which filter, which waveforms are going to be attenuated or seen less the most, it's going to be the lowest number because it's going to stop some of these waveforms from coming through. So again, the higher the number or the larger the number of the low frequency filter, the more the waveforms below it or smaller than it are going to be attenuated. Now, the smaller the number, so if I go from 1 hertz to 0.1 hertz, the smaller the number of the low frequency filters, the more of all the other waves are going to be seen. They're going to be accentuated. You're going to see more of those waveforms. And I'm going to show you some examples to help make it a little bit more clear. Okay. So here is an example of a low frequency filter with different ones. So obviously this is just an eye blink. So here at the top, you'll see I did it a little bit different than the last graph. So please bear with me. Is the smallest number, so 0.05. Then we have 1, 3, 5, then, or 0.5, excuse me. Then I have 1 hertz, 3 hertz, and at the bottom is 5 hertz. So you can see at the very top of the screen that eye blink is a very high amplitude. You're going to see more of that slow wave. Now here at the bottom with the 5 hertz wave, you're still going to see it, but it's going to be lower amplitude because you're only going to see a percentage of that waveform. It's going to appear smaller. It didn't completely eliminate it in this case, but it did make it smaller. Okay, so let's see some more examples about these low frequency filters. Okay, so here's an example of post-stictal slowing afterwards, or it could be, I know it's post-stictal because I got the sample. So here I had this 0.1 hertz low frequency filter on, and you can see all of these slow waves. You can see it, you can see them a lot. Here I turned the 0.5 hertz, so you can see them, they diminished a little bit, not quite as high amplitude. Now we have the 1 hertz, so again, you can see it a little bit more. Now we have the 3 hertz filter on, you're seeing it a little bit less. And now the 5 hertz, it's really starting to filter those waveforms out. Okay, I'm going to move a little bit fast because I'm running out of time. I apologize. So here's another example I took right from there. Here's 0.1 hertz. Here's a low frequency filter of 5 hertz. You can see that you see less of those waves. They are attenuated more with that low frequency filter of 5. They are lower in amplitude. They appear lower in amplitude. Here with the 0.1 hertz, we lowered that number. We really opened them up. You see them. They appear higher in amplitude. So our time constant. So the time constant is inversely related to the low frequency filter, which I'll talk more about on the next slide. But the definition of the time constant is defined as the amount of time it takes for a wave to pass through the filter to fall to 63% of its original value to 37% of its original value, and it's measured in time constant. So what on earth does that mean? So it means depending on the waveform, we need it to fall 63% to get to 37%, and we need the time it takes in seconds for it to fall. Okay. So here's a better visualization to understand time constant. There is an equation for this. We don't have time to go through it, but if you do want to know that equation, please let me know. So you can see the waves on the left here at the top. The taller waveform is a little bit fatter, just looking at it. The bottom waveform is a little bit more sharply contoured. And the reason is you can see that it takes longer for this to fall 63% of it than this because it's a shorter time constant. So I said that on the last slide that time constant is inversely related to low frequency filter, and you can think of this relationship as a teeter-totter. So let's go back to that top right. Just visually looking at it, you can see it has a wider duration. It's looking to the at the right of this waveform, this downward slide, right? It's going to take longer to get to fall 63% of it. Going to the right, this means this waveform occurs when you have a 0.1 hertz filter. So you have a lower low frequency filter on, and you're going to have a longer time constant. And the reason, again, that you want to use a lower low frequency filter so you can enhance those waveforms. You can see more of those waves. Their amplitude is going to be higher. When you have a low frequency filter, you're going to have a longer time constant because it's going to take a longer time to fall 63%. Now, the opposite is true with a 5 hertz wave. So we know a 5 hertz filter is going to attenuate slow waves. It's going to reduce them. We're not going to see as many of those. And it correlates to a smaller time constant. Here is 0.033 seconds to fall from that. So if you're trying to study for your board exams and you're trying to understand the relationship between time constant and filters, because they're going to ask you about which time constant will best enhance this waveform, which one will best attenuate slow waves. This is a great graph to memorize. If you have trouble, I suggest you memorize low frequency filters at 0.1 hertz equals 1.03 time constant, and that's going to enhance the waveforms. Now, if I want to reduce low waveforms, if I don't want to see any sweat or anything like that, we're going to use a higher low frequency filter and a shorter time constant. Okay, so high frequency filters only affect high frequencies. They're also called low pass because they let low frequencies pass through unaffected. Again, they can also be called high cut frequencies because they filter out frequencies set above that value. And we really usually use this filter to filter out muscle artifact. The ACNS guidelines recommend that a setting lower than 70 hertz for the high frequency filter can distort or attenuate spikes and other pathological sharp features into unrecognizable forms. And it can also cause muscle artifacts to resemble spikes. And normally, again, it is set at 70 hertz. And I am going to go a little bit faster just to make sure that we get through everything. So unlike low frequency filters, I told you low frequency filters, the lower the low frequency filter, the more of the waveform you're going to see. The higher the low frequency filter, the more it's going to be attenuated. The opposite is true with high frequency filters. The higher or larger the number of the high frequency filter, the more of that waveform is going to be seen. The smaller or lower the number of the high frequency filter, the more of that waveform is going to be attenuated or seen less. We're going to get rid of that. So here is an example. At the top, you'll see at 70 hertz, then 35, and then 15. And you can see the big difference between the 15 and the 70 hertz. We're really attenuating that waveform. We're not seeing that waveform. It doesn't look as sharp. It doesn't look as concerning. It does still disrupt the background. The second one does, but the first one at the bottom doesn't look too bad. So again, overly aggressively using this high frequency filter can attenuate the height of the high frequency waves and can also change the shape of the waveform, giving you misleading results. So, okay. So here's another example. It kind of hurts my eyes. I should have used a different one. But here you can see the 70 hertz filter is on the left-hand side. And then it went to 30. And then it went to 15. And it looks completely different. I'm sure a lot of you have used, lowered their high frequency filter when you couldn't get your patient to relax. You know, you try to have them open their mouth, not have their teeth touch. And you want to see what's going on behind that. So we do use it. So if you do use the high frequency filters, please make sure that you only use them for a short amount of time so that we don't miss out on anything. Okay, so our 60 hertz filter or our notch filter, also called AC filter for alternating current, it is used to just use a specific frequency. So it's usually 58 to 62 hertz. So it's just really removes just that specific frequency. And here in the US, our electric for alternating current is 60 hertz. In other parts of the world, it can be 50 hertz. And it just helps to improve our recording. But the most common cause of 60 cycle artifact, this is a great board question too, is unequal electrode impedances. Your common mode rejection ratio, it can't work. So please make sure that you use your 60 hertz as a last resort. You try everything else first. But again, the main culprit for 60 hertz is unequal electrode impedance. So please make sure that they are balanced, they are equal, and they are within limits. And again, here is two examples of one with the notch off and then one with it on. So it looks a lot cleaner with that notch on. Okay, so phase shift. So filtering, when you filter the waveforms, they can impact the timing of those waveforms. So if we excessively use our high frequency filter, our fast frequencies can lag behind in time. If we excessively use our low frequency filter, those slow frequencies can appear earlier or lead in timing. So the lower the number, the later the time of the waveform. Okay, so what do I really want you to take away from these filters? So for your low frequency filter, what's really important for you to know that the lower the number, the low frequency filter, the more of that waveform is seen. The higher the low frequency filter, the more of the waveform is attenuated or seen less. Time constant is inversely related to low frequency filters. So if you have a time constant question, automatically eliminate anything with a high frequency filter because it's only going to affect those low frequencies. So for time constant, the shorter the time constant and eliminates those slow waves, you're going to attenuate them. You're going to see them less. The longer the time constant, the more slow waves you're going to see, the higher the amplitude they're going to appear. For a high frequency filter, I want you to know that the smaller the number of the high frequency filter, the more of the waveforms are attenuated, right? So the smaller the high frequency filter, the more are attenuated. The larger the high frequency filter, the more those waveforms are seen, more let in. For your notch, your 60 hertz or 50 hertz, it's supposed to only be used as a last resort, and most of the time it's because of unbalanced influences. Okay. So I know we're running a little bit on time, so I'm going to kind of go quickly. So here, what I want you to do is just kind of think about it, and then we'll have a couple polling questions in a minute, but just to kind of make sure that you're grasping some of these and giving you some examples. When would we increase our low frequency filter? So when would we change our low frequency filter from 1 hertz to 5 hertz? When would we do that? Well, we would do that to get rid of pulse artifact, sweat artifact. Theoretically, when there's a spike in wave, to better see the spike if we really wanted to, so we get rid of that slow wave. So those are reasons we would want to get rid of those slow waves. We would change it from 1 hertz to 5 hertz. So now think about it. When would we decrease the low frequency filter? When would we change it from 1 hertz to say 0.3 hertz? When would you want to do that? Well, we would want to do it when we want to enhance the slow wave. We want to make that slow wave have a higher amplitude. We want to see a higher percent of that wave, maybe 100% of that wave, right? So if there's a tumor, a brain bleed, any slow wave focus, if you have a neonate, they have more slow waves, we would want to change that filter. We would want to lower it to let more of those frequencies in so we see a higher amplitude of those waveforms. Okay, so when would we lower our high frequency filter? So when would we change our high frequency filter from 70 hertz to 30 hertz? Well, we would change it after we tried to get the patient to relax. Of course, we want them to relax first. We want to change it as a last resort, and we only want to change it for short periods of time. Okay, so when would we increase our high frequency filter? So change it from 70 hertz to 100 hertz to allow more of those high frequency waves in so they appear larger in amplitude. Well, really to enhance gamma waveforms and other things. You don't do it a lot. If you're doing research or if you're at an epilepsy center and you're doing HFOs and different things, you may change that. Okay, and when do we use our 60 hertz filter? When would we use that? And again, we would use that as the last resort after all other measurements have been filled. And again, check all that. And then we're going to get to our polling questions. Polling question number 5. So I'll let you guys see it on the screen and think about it.
Okay, we're going to launch the same question and see what our audience thinks of this one. Okay, we have a pretty good response. Let's close this and let's share the results. Here they are.
Okay, so we have somebody answered a little bit of everything, which is good. But the majority of you got it right. Which of the following filter settings will record the greatest amplitude of a 0.4 hertz wave? And the correct answer is 0.01 hertz. So again, the lower the low frequency filter, the more of those slow frequencies will be seen. Therefore, we want the lowest number. Think of a number line to allow more of the voltage of the slow frequencies to be seen. So very, very good job. Okay, one more. We're going to do polling question number 6. Which of the following time constant settings would best reduce sweat artifact?
See what we think here.
Yes, so remember what time constant is related to.
Okay, excellent response. Great response. Let's see what we have here. All right.
Okay, so we are a little bit of everyone. So which of the following time constants would best reduce sweat artifact? Well, again, we see it. The actual answer is 0.3 seconds, right? So the lower the time constant, the slower waves are more attenuated, right? So the lower the time constant, the more those waveforms are attenuated. So we had some people with 5 seconds. That's incorrect. The longer the time constant, the more of those slow frequencies are let in, right? 1 second, again, very long. 0.5 second, it's close, but there is the better answer. So again, the smaller the number of the time constant, the more of those waveforms are attenuated. I'm sorry, attenuated, because you have a shorter part. So I just reversed that. So again, 0.3 seconds, because the lower the time constant, the more those waveforms are attenuated. It's inversely related to that low frequency filter. So the shorter the time constant, the bigger the low frequency filter. So it would equivalent to about 5 hertz. So we're going to get rid of that sweat artifact. So very good job, everybody. Here are some of my references. Thank you so much. I apologize. We had some technical issues and we went over on time by a little bit. So thank you so much for bearing with me. I hope you guys learned something. If you have any questions, you can feel free to email me. I guess I can put my email in the chat.
Chat, or they can email the Neuro Academy.
Oh, perfect.
Let's take one question here before we go. This is an interesting. Okay. Let's take one question. If you select the 7 microvolt per millimeter sensitivity in the digital recording, does the software automatically make the adjustment to display exactly 7 microvolts per millimeter, regardless the number of channels displayed?
Yes, it should. So that's what's great about technology, and you have to love it. It automatically does it. Now, what's great, it changes everything that's with EEG, depending on the brand. So it would automatically change that. And then there's different tools, especially even with native, that it will actually measure the voltage with you. And if you would just change one channel, it would highlight that. But yes, it automatically does all that for you. And it will actually even measure the waveform and give you the voltage. It will actually calculate it for you as well. But yes, great question.
Okay, well, thank you. Well, this about will conclude our webinar for today. I would like to thank Melissa Strewing for her excellent and informative presentation, and you, our audience, for your participation. Please contact us via email should you have any questions regarding today's webinar. And also, we haven't addressed your question. Please email it to us, to the Neurotraining Academy, and we will get Melissa to answer you personally. For access to future events and all other educational programs in NATIS, I invite you to join our new Neurotraining Academy. The registration is free. Just visit our website or sign up at neuro-training.academy. So on behalf of NATIS and our Neurotraining Academy, thank you again for joining us today, and we hope to look forward to seeing you next time. Thank you.